What's up, everyone? In this video, we're going to be talking about differentiability. So differentiability is just asking the question, can we take the derivative of a function? Kids, if we pick a specific point, can we take the derivative there? Does it exist? Is it a well-defined number? Can we say what it is? Like the derivative is 3 or a -6. Because not all functions have a derivative at every point. There are some weird functions or weird situations where the derivative might not exist. So the kind of question you get asked on an exam or AP Calc test is, hey, look at this function. Can you tell me if the derivative exists here? If it does, what is it? If it doesn't exist, why not? So that's what we're going to talk about today. So to start thinking about this idea, I want to just look at these 3 functions that I have drawn here. And so think about, for example, this first function, if we're looking at the point x equals 2, so right where that open circle is, would we be able to take the derivative there? And if we can, what would it be? And if not, why not? So we have this little hole here. We have this removable discontinuity. So that, might affect things. Maybe, because there's that removable discontinuity there, the derivative might not exist. That's what we're going to find out. And in this one in the middle here, let's say we wanted to take the derivative right at x equals 3. So where this little kind of the top of the triangle is. And so again, what would be the derivative there? If you think the derivative exists, then you should pause the video and think about it. Like, can you come up with a number? Can you tell me exactly what the slope of the function would be at that little kind of cusp point? And then this other function, if we look at x equals -4, we can see that we have this jump discontinuity. So we have the gap in a function. So, what would be the derivative at that point? Would we look at this piece to find the derivative, or would we look at this piece? These are all questions that you should think about and try to come up with your own answer to them. But I will spoil it and tell you the answer now. So whenever we're trying to figure out if a function is differentiable, there are 2 conditions that must be satisfied in order for the function to be differentiable. If one or both of these conditions are not satisfied, it's not differentiable. Okay, so please memorize these conditions. Just memorize them in the wording I have written here because you probably will need them for the AP test. So the first condition is that the function must be continuous at the point you're trying to take a derivative at. And then the second condition is that the function has to be smooth at the point you're trying to take a derivative. If both of those things are satisfied, you're good, it's differentiable. If it's not continuous, then it's a no-go, there's no derivative. And if it's not smooth, also no derivative exists. So I'm going to talk about now, what does it actually mean to be continuous? What does it mean to be smooth? So for continuous, I do have a video on it. So if you want to go into more detail on it, go watch that video. But roughly, continuous means that there are no gaps in the function. So that means if you put your pencil down on the paper, you can draw the entire function without picking your pencil up off the paper. So these 3 functions right here are examples of continuous functions because it's just one big movement. They're all kind of connected by one line. You can draw the whole thing without picking your pen up. There are no gaps. So these functions are continuous. These red functions here would be example of functions that are not continuous. So this first one, there's a hole right here. So you would have to pick your pencil up off the paper for that hole. So therefore it is not continuous. This one right here has a jump discontinuity. There's obviously a big gap in the middle of the function. So that is not continuous. And this one over here, it has a vertical asymptote right here. And so if it has a vertical asymptote, you can't draw the whole thing with just one movement of your pencil, right? Because the function can never cross the vertical asymptote. It can't physically go over the vertical asymptote. So you have to pick your pen up off the paper and then put it back down on the other side of the vertical asymptote. So that is not continuous. And then when it comes to smooth, a rough definition of what smooth means is that if you look to the left of the point that you're interested in and then to the right of the point, if you compare the slopes between those two to the left and to the right, the slopes will be relatively similar. So I'll explain what I mean by that, but one thing I want to point out is that this is not like a technical definition, so please don't think that this is what you would find in a textbook. Both continuity and smooth have very technical definitions. However, I don't want to teach them because I really don't think you need to know know them for AP Calc. So these rough kind of ideas of what it means to be smooth are okay. But just, don't try to quote me on matching a textbook because I know it doesn't match. So for smooth, what we mean by that is, there's no sharp corners, everything's kind of nice and round. And then if we look at a certain point, if we look to the left of it and to the right of it, the slopes are similar. So what I mean by that is like all these functions right here in green are smooth. And so if we look at this kind of upside down parabola, if we look at the peak, so this point, that's kind of like the top of the hill right there. If we look at that, that point is differentiable because if you go just to the left of that point, the slope is positive, but it's really shallow, right? The slope's really small. It's like almost flat. The slope's maybe 0.1 or something. And then if we look to the right of the peak, the slope's negative, but it's still a really shallow negative. Maybe it's like negative 0.1. So the slopes to the left and to the right are like pretty close. So that means that this function is smooth. And then if we look at these other two green functions here, again, you can see it's like nice and round. The shape, it has these nice round features to it. There are no sharp edges. So you do have to use a bit of intuition when you're figuring out if something's smooth. But, I think you can trust your intuition here. Like if something looks sharp to you, then it's probably not smooth. And if it looks nice and round to you, then it probably is smooth. So in red right here, these are kind of some functions that would not be smooth. And so hopefully it's kind of obvious to you, like this one, it has that really sharp cusp. It comes to like a very distinct point. So that is not smooth. And if you look at the slopes to the left of the peak, those slopes are positive, but they look pretty steep, right? Maybe the slope is like 10, 20, maybe 30. And then if you look to the right of this peak, the slopes are negative, but they're like pretty negative, right? The slopes may be like negative 10, negative 20, negative 30. So the difference in the slopes on the left and the right is pretty big, right? The slopes on the left are like maybe 20, slopes on the right are negative 20. That's a huge difference, right? So that's kind of your sign right here that this would not be considered smooth. Same with this one, there's this corner piece, so that is definitely not smooth. And then this is, it's kind of like you have triangles going on and they have that sharp point at the top and bottom of them. So, kind of just trust your intuition when you look at the picture. For the most part, especially in AP Calc, it'll be kind of obvious, right? If it looks sharp to you, like it probably is. And if it looks nice and smooth, then it should be fine. So now I'm going to do an example here, and we're just going to decide if each of these functions are differentiable at the points indicated. So remember, for it to be differentiable, it has to be continuous and smooth. So we need to check both of those things. So if we look at this first function right here, let's see, is it continuous? Yeah, it looks continuous, right? Because I can draw the whole thing without picking my pen up off the paper. So continuous looks pretty good. What about smooth? Well, we want to figure out if it's differentiable at x equals 3. So that's kind of the point that we're concerned about. So let's look at that. Does that look smooth to you right there? Probably not, right? I mean, that's like kind of a sharp corner. So just based on intuition, it looks sharp. So we can go ahead and say that that is not smooth. So since it is not smooth, we can conclude that this function then is not differentiable at x equals 3. So that is because we didn't satisfy both of our criteria. It is continuous, that criteria was satisfied, but remember we need to satisfy both criteria. So since we did not satisfy both of them, it's not differentiable. If we look at this next function right here at x equals 4, it looks like it's definitely continuous, so we can go ahead and check that off. And then what about smooth? Well, this one looks nice and round. It doesn't look like there are any sharp corners anywhere. So we can go ahead and say that that is smooth. So since it satisfies both of our criteria, we can say that it is differentiable. So this function is differentiable at the point x equals 4. Now let's look at this last function here. First thing we want to look at, is it continuous? And right off the bat, we can tell that at x equals 3, it's definitely not continuous, right? There's that big jump discontinuity. There's a huge gap. It is not continuous. So since the first criteria was failed, we can immediately say it's not differentiable. So this one is not differentiable, and that is because that first criteria was not satisfied. So those are some examples for you. And when it comes to deciding something's differentiable or not, as far as AP Calc goes, it's really just kind of a matter of looking at the picture and just deciding based on that. And then the last thing I want to talk about is just a little bit of a wording thing that confuses students sometimes. So when you're asked about this differentiability question, the question might be phrased differently. So they might ask you, is the function f of x differentiable? Or they might ask you, is the function f of x differentiable at x equals a? So there's a slight difference in the wording between these two. So for the first one, if they ask you if the function is differentiable, that means they're asking you, is the entire function differentiable? So in order to answer yes to that, the function would have to be differentiable at every single point, okay? So in order to say, yes, the function's differentiable, it needs to be differentiable everywhere. However, if they ask you, is the function differentiable at x equals a, that means they only want to know what's going on at that point x equals a. So you don't need to look anywhere else on the function. You just need to look at that one point x equals a and determine if it's continuous and smooth. So if it is, then you can go ahead and say, yes, it's differentiable there, regardless of what the function's doing everywhere else. So even if the function's doing some wacky, non-differentiable stuff at other places, you don't care about that. You only care about what's happening at x equals a. So hopefully that makes sense for differentiability. Of course, if you have any questions, please leave those in the comments and be sure to like and subscribe because that really helps me out. Thanks.